Welcome to today's deep dive.
Right.
We're really thrilled you're joining us
Yeah, absolutely thrilled to be here.
because, if you're listening to this right now, you're probably the kind of person who is just intensely curious about how complex systems actually function.
All right, beneath the surface.
Exactly, beneath the surface.
Yeah.
But, you don't necessarily want to drown in a sea of technical jargon.
Or like dense academic papers,
Oh,
right?
yeah.
Those can be so dry.
Oh, totally. You want the insight, the edge, that kind of aha moment.
Yeah, the practical takeaways.
And that is exactly our mission today. We are going to explore the dangerous, incredibly costly illusion of a very specific phrase.
A phrase we all use, by the way.
Oh, yeah. You've probably used or heard this week in your own work.
Yeah.
And that phrase is, it's still running.
Which is, a phrase that brings immense psychological comfort.
It really does.
It does. Because from a neurobiological standpoint, our brains just love binary states.
Right, which is exactly how we usually look at a machine or, a software deployment, or even our own bodies.
Yeah, we expect things to act like a light switch.
Exactly. You flip it, the light is on, and it's working.
Or the bulb is dead, it's broken, and you replace it. Clean and simple.
So simple. But as soon as you step onto a complex manufacturing floor,
Oh, boy.
right, or if you look at intricate cloud software operations, that clear binary completely falls apart.
It shatters.
It really does. You're suddenly looking at this operational landscape that is murky, filled with things that are, technically operating, but definitely not normal.
The space between perfectly normal and catastrophically broken is just vast.
That's massive.
It is. If you imagine the backdrop of our conversation today as this subtly shifting industrial control room, screens blinking, data flowing.
The faint hum of heavy machinery coming up through the floorboards.
Exactly, that hum. You realize that today is really about learning how to read the quiet signs before the loud alarms go off.
Okay, let's unpack this. To do that, we have an incredible stack of sources today.
A really diverse stack, too.
Yeah. We are pulling from industrial safety frameworks, from astronauts. We've got exhaustive economic data on manufacturing machinery from the National Institute of Standards and Technology.
NIST.
Right,
Yeah.
NIST. And we have these brilliant behavioral psychology essays on tech culture by the analyst Dan Liu.
Those are fascinating.
They really are. Plus, we also have this cutting-edge literature on predictive operational safety engineering, or PAE.
Which sounds intimidating, but we'll break it down.
We will. And we're grounding all of this in
Billions. To truly understand the financial and physical stakes of ignoring that murky middle ground, we really have to look closely at how the NIST data categorizes machinery maintenance.
Okay, how do they break it down?
So they break it down into 3 distinct strategies. First, there's reactive maintenance.
Right.
This is your classic run-to-failure model.
Meaning you just wait for it to break.
Exactly. You do absolutely nothing until the equipment physically halts, and then you just scramble to fix it.
Which, sounds incredibly archaic, but it's shockingly common, isn't it?
It's extremely common. You'd be amazed. Then second, there is preventive maintenance.
Okay, so that's different from predictive.
Very different. Preventive is strictly scheduled or time-based.
Like an oil change.
Yeah, exactly, like changing the oil in your car every 5,000 miles, regardless of whether you drove those miles on a pristine, flat highway or if you were towing a heavy boat up a dusty mountain.
Right, the schedule doesn't care about the context.
Exactly. And finally, the third strategy is predictive maintenance.
Which is the goal here.
Right. This is condition-based. It relies on continuously observing actual data. So temperature, acoustics, vibration.
To see what's really happened.
Yeah, to calculate and predict a failure horizon before it actually happens.
The numbers NIST gathered on how much U.S. manufacturing spends across these strategies are just staggering.
They really put it into perspective.
Just looking at 2016, U.S. manufacturing maintenance expenditures were $57.3 billion.
That's a massive budget.
Huge. But the losses due to preventable issues, issues that predictive maintenance could have caught, were more than double the actual maintenance budget.
Let that sink in.
We are talking about $119.1 billion in preventable losses in a single year.
And diving into the anatomy of that 119 billion reveals the true nature of industrial inefficiency.
How so?
Well, about 18.1 billion of that was lost directly due to downtime.
So that's just the sheer cost of idle labor and halted assembly lines.
Right. People standing around, machines not moving. But a massive $100.2 billion was due to lost sales stemming from delays and defects.
Wait, I want to pause on that 100.2 billion figure because I think it fundamentally shifts the perspective on what a breakdown actually is.
Oh, absolutely.
Because when a machine is running to failure, it isn't just operating perfectly until the exact second it dies.
No, not at all.
It is degrading. And as it degrades, the quality of the product it's manufacturing is degrading right alongside it.
That is the insidious nature of the still running illusion.
Yeah.
Let's say you have a precision CNC mill, right? Shaping aerospace components.
Okay.
A bearing starts to wear out. The machine doesn't stop. It just keeps milling.
But the precision is gone.
Exactly. Now, instead of a tolerance of 1/10,000th of an inch, the vibration causes a variance of 3/10,000ths.
Which in aerospace is a huge deal.
It's scrap. You just produced 500 defective parts before the machine finally sees.
Unbelievable.
You've wasted raw materials, energy, labor, and if those parts make it to the customer, you've destroyed your supply chain reliability.
Not to mention the human toll. The NIST data isn't just about dollars and cents.
No, it's much darker than that.
They estimated that 16.03 injuries and 0.05 deaths per million employees were directly associated with preventable maintenance issues.
Which transforms this from, a simple ledger problem into a profound moral imperative.
Absolutely.
It creates a highly dangerous operational cycle. When a facility waits for a failure, they force their operators into high-stress, emergency repair situations.
Right, because everything is on fire.
Yeah, you have people working frantic overtime, maybe bypassing standard lockout, tagout safety procedures because the line manager is just screaming about lost revenue.
And that chaotic environment is precisely where accidents spike.
Without fail.
The NIST data also gives us a clear A/B test between facilities, showing this wild contrast.
The numbers are stark.
The facilities sitting in the top 25% of relying on reactive maintenance suffer 3.3 times more downtime than their peers.
3.3 times.
And they produce 16 times more defects.
That's the degradation we were talking about.
Right. And they see a 4.9 times increase in inventory.
Now, that inventory metric is critical.
Why do reactive facilities have almost 5 times the inventory?
Because they have to hoard spare parts, right? And excess finished goods, they have to buffer against their own constant, unpredictable breakdowns.
Oh, that makes sense.
It's an incredibly inefficient use of capital. You just have cash sitting on shelves. Meanwhile, the top 50% of facilities that rely heavily on predictive maintenance see an 87% lower defect rate.
87%. But I have to challenge this narrative slightly, though.
Sure, go ahead.
The NIST data shows predictive maintenance is clearly superior in outcomes. But the reality on the ground, especially for anyone listening who manages physical assets or IT infrastructure, is that upgrading legacy systems requires massive capital expenditure.
Oh, the upfront costs are real.
Right. We're talking millions in industrial Internet of Things, sensors, network infrastructure, massive data storage.
And hiring specialized data scientists.
Exactly. Before a single actionable predictive insight is even generated. How does the data justify that initial massive hurdle? I mean, it sounds like you're asking me to buy an MRI machine for my car instead of just waiting for the check engine light.
What's fascinating here is that the return on investment for predictive systems actually eclipses those massive setup costs relatively quickly.
Really? How quickly?
Well, the NIST report calculated the perceived economic benefits of adopting predictive maintenance strategies at $73.8 billion.
Wow.
Yeah. That comes from $6.5 billion in downtime reduction and a massive $67.3 billion in increased sales capacity.
So they aren't just saving money, they're making way more.
Exactly. Facilities relying on predictive maintenance transcend being mere cost competitors. They become market differentiators.
Because they're more reliable.
Right. They can guarantee delivery times and quality because they have mathematically stripped the uncertainty out of their production schedules.
That's a huge advantage.
It is. The initial CapEx for condition monitoring technology pays for itself by preventing the catastrophic secondary damage, both mechanical and reputational, that occurs when a machine runs until it destroys itself.
Okay, so we've established that waiting for the metaphorical check engine light is financially ruinous and actively dangerous.
Yes.
The imperative is to catch things early, but that requires us to totally rethink the timeline of a breakdown.
You have to completely shift our mental model.
Because a massive industrial chiller doesn't just spontaneously decide to break one Tuesday at 2 p.m. There is a distinct physical degradation curve.
Absolutely. Our sources from Traction and GroundUp.ai, which specialize in advanced condition monitoring, they map out this failure timeline meticulously.
And it's fascinating how it unfolds.
It really is. Different physical signs manifest at very specific points on the degradation curve. And, the most common metric people monitor,
Which is heat, right?
right, heat. Heat is actually a deeply lagging indicator.
That is such a crucial paradigm shift because we instinctively think, oh, if it's running hot, we caught the problem.
But GroundUp.ai stresses that by the time a machine is generating excess heat, the internal damage is already severe.
The friction has already overcome the lubrication. The metal is already warping.
Exactly. Heat isn't the opening act, it's the finale.
So what is the opening act?
The opening act is acoustic, specifically ultrasonic.
Ultrasonic.
Yeah. The very first sign of a developing fault is high-frequency acoustic emissions caused by microscopic friction.
So this is happening long before the metal starts to visibly warp.
Long before. It's the sound of a microscopic imperfection in a ball bearing scratching against its housing.
And we can't hear that, obviously.
No, these sounds are completely outside the range of human hearing.
GroundUp.ai points out that every single machine has a unique sound fingerprint.
Yes, a unique acoustic profile.
So if you map that fingerprint when the machine is healthy, you can detect the absolute earliest deviations.
Precisely. And following that ultrasonic phase, as the fault progresses down the curve, then you start to get audible sound changes.
Like a new rattle or a hum.
Right. Something an operator might actually hear with their own ears. Then comes physical vibration, measurable by accelerometers.
And then finally, heat.
Finally, at the very end of the curve, you get heat and smoke. So if a facility relies solely on infrared thermography or standard temperature gauges, they have a massive blind spot during the cheapest, easiest intervention window.
But how do you practically monitor that, though? I mean, factories are incredibly loud.
They're deafening. So how does a sensor isolate the microscopic scratch of one tiny bearing from the ambient roar of 300 other machines?
That is the realm of industrial AI and digital twins.
Okay, break that down.
The AI isn't just like listening with a dumb microphone. It uses mathematical techniques like fast Fourier transforms to break down the raw, chaotic audio signal into individual frequency components.
So it filters out the noise.
Exactly. It separates the persistent, low-frequency hum of the factory floor from the anomalous high-frequency spike of that specific bearing.
Oh, that's clever.
And it continuously compares that live feed against a baseline synthetic model, the digital twin of that exact machine operating perfectly.
Which perfectly sets up this academic preprint we reviewed on POS.
Right, predictive operational safety engineering.
Right. Because if AI can hear the microscopic friction, POZ provides the mathematical framework for what to do with that information.
Because data without a framework is useless. Exactly. It argues that we need to move industrial safety from a reactive question of what just happened to a predictive question of how much safe time remains.
Which is a profound shift in engineering. Traditional safety architecture is fundamentally a feedback loop.
Meaning it reacts to the past.
Yeah. A variable like tank pressure crosses a hard limit, a sensor trips, an alarm sounds, and a human or automated system reacts to bring the pressure down.
But POSE is different.
POSE introduces a feed-forward mechanism. It looks at the trajectory of the degradation and calculates safety as a continuously eroding state.
The sources outline a massive conceptual bridge here, moving from RUL, remaining useful life, to RSOT.
Remaining safe operating time.
Right. What's the real difference there?
Well, RUL is highly equipment-centered. A predictive algorithm might look at a failing pump bearing and say, this asset has an RUL of 400 hours before it seizes.
Okay, which is useful for the maintenance team ordering a spare part.
Sure, but RSOT is process-centered and fundamentally safety-driven.
So it's looking at the big picture.
Exactly. It asks, given that the bearing is degrading, how is the resulting drop in fluid pressure affecting the cooling capacity of the downstream chemical reactor, and how long before the entire collective operation breaches a safety boundary?
So RSOT is aggregating the ripple effects.
All of them.
It's taking into account the failing bearing, the fluid temperatures, the pressure levels, and even the availability of backup safeguards.
Yes, all those variables.
And synthesizing that into one predictive timeline for the whole system.
And it pairs that timeline with the Operational Vulnerability Index, or OVI.
Okay, what is OVI?
OVI is a calculated metric that multiplies the rate at which you are losing your safety margin by the severity of the potential consequence. And then it factors that against the availability of your automated safeguards,
So instead of a control room operator looking at a wall of 200 flashing amber lights.
which causes alarm fatigue.
Right, exactly. The OVI calculation synthesizes all of that and says, look, pump 4 is vibrating and valve 7 is sticky. But based on the system's trajectory, this specific combination means reactor B is going to go critical in exactly 42 minutes. Intervene here.
It quantifies and prioritizes the urgency in a landscape of overwhelming data.
To really visualize how these systems mask their own deterioration,
Yeah.
our sources described a conceptual industrial training video.
Oh, this is a great example.
It's known as the expanding correction. Have you seen this?
I have. It's brilliant.
So for the listener, picture a beautifully clean, perfectly organized, compressed air utility room. A worker steps up to a large master pressure dial and turns it up by just one small click.
Just a tiny adjustment?
Just one click. But immediately, the camera shows the consequences rippling through the entire facility. A main gauge rises, flexible hoses get slightly firmer.
The tension increases everywhere.
Yeah, an air nozzle on an assembly line blows a bit harder. Another pneumatic tool, completely unrelated to whatever prompted the dial turn, suddenly gets an aggressive boost in pressure.
It's systemic overcompensation.
Exactly. And then the camera slowly tracks down one small secondary branch of dirty pipes in a dark corner to reveal the actual root cause. A tiny, partially closed, rusted isolation valve.
The visual brilliance of that scenario is that it perfectly encapsulates how interconnected everything is. The entire factory is being subjected to higher stress and accelerated wear and tear because of one overlooked microscopic restriction.
It's the industrial equivalent of having a bad knee.
Oh, that's a good analogy.
Right. You tweak your knee playing tennis, you don't rest it, you just walk with a slight limp. You overcompensate.
You adjust your posture.
Yeah, your gait changes, your hips get out of alignment, and 3 weeks later you bend over to pick up a drop pen and your lower back goes out in agonizing, paralyzing pain.
And you think your back is the problem.
Exactly. The loud alarm is the back pain, but the root cause, the early weak signal, was the knee.
The knee analogy works perfectly for the mechanical physics of the situation. But what makes a factory floor or a software deployment or a hospital ward so much more complex than a knee is that you have a brain involved that can actively choose to ignore the limp.
What do you mean?
You have human operators.
Right. Which brings us to the most frustrating question of this entire deep dive.
The human element.
We have ultrasonic sensors that can hear a pin drop in a hurricane. We have AI that runs fast Fourier transforms to isolate bearing friction. We have COFUs calculating our remaining safe operating time down to the minute.
The technology is practically clairvoyant.
Right. So why did a chemical plant in Texas still have a catastrophic leak last year? If the machines are whispering their secrets, who is putting their hands over their ears?
Well, the answer lies in human psychology. Specifically, the phenomenon known as the normalization of deviance.
This concept was coined by the sociologist Diane Vaughan, right?
Yes, during her exhaustive investigation into the 1986 Challenger space shuttle disaster.
Such a tragic but vital case study.
It is. She studied how NASA engineers slowly, over multiple missions, grew accustomed to the rubber O-rings on the solid rocket boosters sustaining thermal damage during launches.
According to the original design specifications, any damage to those O-rings was totally unacceptable. A zero-tolerance safety boundary.
Absolutely zero tolerance. But on early flights, they noticed minor erosion.
And the shuttle still made it to orbit and returned safely.
Right. So because the damage hadn't caused a catastrophic failure yet, the definition of acceptable risk subtly expanded. The anomaly became categorized as an in-family issue.
So the deviance became normal.
Exactly. It is the insidious, gradual process by which unacceptable practices or declining standards become perfectly acceptable just because they haven't resulted in a disaster yet.
It's like playing Russian roulette and thinking you're safe because the first 2 chambers were empty.
That's a dark way to put it, but yeah. And Vaughn pointed out that this wasn't malicious negligence by NASA. It was a structural, cultural blindness.
It's just how human brains work.
From a neurobiological perspective, the human brain is hardwired for sensory adaptation. If a stimulus is constant and doesn't immediately result in pain or death, our brains actively filter it out to save cognitive processing power.
So translate that to the factory floor. An operator hears a new rattle in a conveyor belt. They tweak a tension dial to compensate.
The belt keeps moving.
Right. The shift meets its production quota, and the operator gets a high five from the floor manager for hitting their numbers.
So the culture inadvertently rewards the deviance,
And the machine's status remains logged simply as running.
which hides the danger. The tech analyst Dan Liu wrote some brilliant essays exploring how this exact psychological trap manifests in software engineering and corporate culture, too.
Oh yeah, he describes a phenomenon he calls the new person WTF cycle.
Which is a universally recognizable experience for anyone who has ever changed jobs.
Right. You join a new company, you're eager, you're fresh, and on week one, you look around and see something functionally insane.
Every company has something.
They do. Maybe their code version control is entirely manual, or the HR onboarding process leaves new hires without a laptop or email access for 3 weeks.
And you're just sitting there, confused.
Yeah, you look at your new coworkers and say, WTF is this?
And the veterans look at you with tired eyes and say, yeah, we know it's a huge pain, but we've tried fixing it and it's impossible. It's just how it is.
So you build a workaround,
Yeah.
you adapt,
Because you have to.
right? And then 6 months later, another new person joins. They look at the broken system and say, WTF. And you are the one who looks at them and says, yeah, we know, it's fine.
You have fully normalized the deviance.
It's so true.
Liu's essays provide incredible, granular examples of this in high-stakes environments. He details companies with multi-hundred-million-dollar operating budgets that take 3 months and 7 layers of vice presidential approval to authorize a software license that costs $200.
Which is just absurd.
The bureaucracy is functionally broken, but everyone just shrugs and accepts the paralysis.
My favorite, and by favorite I mean most terrifying example Liu gives, is about a specific Python programming library called @Flaky.
Oh, the @Flaky library.
Yes, which became incredibly popular in Silicon Valley.
Now, the intent behind that library makes sense on paper. In massive code bases, you sometimes have software tests that are genuinely unpredictable due to complex network timings or third-party API dependencies.
So they aren't actually broken, just flaky.
Right. The @Flaky decorator was designed to flag those specific tests, so developers knew they might occasionally fail for reasons outside their control.
But the implementation became a masterclass in normalizing deviance.
It really did.
Instead of using it to flag unpredictable tests for later repair, developers started using the @Flaky library to command the system to automatically rerun a failing test multiple times in a row.
Just forcing it through.
Yeah. If the code failed 3 times but happened to pass on the 4th try, the system recorded it as a pass and the developer merged the code.
They literally wrote a program to automate the normalization of a failing system.
They codified the "it's still running" illusion.
Because if you only look at the final output, a green check mark on the test or a widget rolling off the assembly line, you are completely blind to the chaotic mechanical or digital negotiation happening underneath.
But let's look at this from the perspective of an individual worker. Okay.
Sure.
If I'm a newly hired operator on an assembly line, and my veteran supervisor who's been there for 20 years and knows everyone from the plant manager to the union rep tells me a weird new vibration is just how the old girl purrs.
How are you supposed to push back against that?
Exactly. I don't want to look like a troublemaker or someone who is overly anxious. I certainly don't have the political capital to hit the emergency stop button and shut down a line that generates $50,000 an hour.
If I connect this to the bigger picture, you've just articulated exactly why relying on individual courage is a failing safety strategy.
It's too much pressure on the individual.
Way too much. You cannot expect a junior employee to consistently fight human nature and hierarchical pressure. Diane Bond's research highlighted that a lack of psychological safety guarantees that people who observe weak signals will not speak up.
They'll just keep their heads down.
Furthermore, if leadership has a historical pattern of diluting reports, ignoring warnings, or punishing the messenger to protect production metrics, the workforce learns to stay silent.
So what's the solution?
To protect an organization from its own adaptive blindness, the system itself must be engineered to remove the social friction of reporting. The framework must demand the recording of weak signals as a routine, unpunishable act.
Which transitions us into the absolute danger zone for these weak signals.
The danger zone.
The psychological blind spots of an individual are dangerous enough, but they become deadly when they have to be transferred across a team.
Absolutely.
The ultimate stress test for operational safety, the exact moment these weak signals are most likely to be dropped, misinterpreted, or forgotten, is the shift handover.
Without question. Shift handovers are the most vulnerable moments in any continuous 24/7 production environment.
Like anywhere.
Anywhere. Whether it's a petroleum refinery changing crews at 6:00 a.m. or a hospital nursing staff rotating at 7:00 p.m. If the outgoing team does not explicitly structurally log the minor workarounds they instituted or the subtle new acoustic changes they noticed.
The incoming team is effectively flying blind.
Completely blind.
A report we analyzed from TeepTrack introduces a great term for this: invisible losses in OEE.
Right. OEE, or overall equipment effectiveness, is the gold standard metric for manufacturing productivity.
Break that down for us.
It multiplies three factors: availability, performance, and quality.
Okay, so if a machine is scheduled to run for 10 hours but is down for 2, its availability takes a hit.
Correct.
If it's supposed to make 100 parts an hour but only makes 80 because it's vibrating, performance drops.
Right, again.
And if 10 of those parts are deformed, quality drops.
Precisely, and poor shift handovers create massive invisible losses in the performance and quality metrics.
How does that happen in practice?
Well, imagine the outgoing shift knows the CNC mill has a quirk today, right? They know you have to manually adjust the coolant flow every 20 minutes to prevent overheating.
But they don't document it.
Exactly, because to them, it's just a temporary nuisance. They clock out, the incoming shift takes over, runs the machine at standard settings, and 2 hours later, the tooling bit shatters, destroying a $10,000 aerospace part.
All because they didn't pass along the context.
The loss is entirely rooted in the communication gap.
History is littered with catastrophic examples of this exact failure mode. The most infamous is the Piper Alpha oil rig disaster in the North Sea in 1988.
Which cost 167 lives.
Yeah. It remains the deadliest offshore oil disaster in history.
And the root cause of Piper Alpha was an escalating series of systemic failures, but the inciting incident
Was a botched shift handover.
yes, regarding a critical piece of safety equipment.
Just to give a brief overview, during the day shift, a pressure safety valve on a condensate pump had been removed for routine maintenance. Because the work couldn't be finished before the shift ended, the workers temporarily sealed the open pipe with a blind flange, just a flat metal disc.
Which meant that piece of equipment was now highly dangerous if operated.
Exactly. But that absolutely critical piece of information was not effectively communicated to the incoming night shift control room operator.
The permit-to-work system was disorganized. The physical paperwork was misplaced.
Oh, that happened.
When a different pump tripped during the night shift, the new control room operator, totally unaware of the missing safety valve, authorized the activation of the compromised pump.
Because they thought it was perfectly fine.
Yeah, the blind flange couldn't handle the immense pressure, the highly volatile gas leaked, and a cascading series of explosions destroyed the platform.
It's just devastating. And the 3 Mile Island nuclear incident in 1979 also had deep systemic roots in handover failures, where equipment status and valve positions weren't accurately passed along.
These aren't just industrial anecdotes. They're case studies in how undocumented deviations kill.
Which is why high-reliability organizations like nuclear submarines, commercial aviation, and elite medical teams use rigidly structured communication protocols.
Right, they'll just wing it.
One of the most effective, originally developed by the military and widely adopted in healthcare, is the SBAR framework.
SBAR, situation, background, assessment, recommendation.
It's so simple but so effective.
It forces the outgoing person to cognitively structure their thoughts and strip away ambiguity. Situation. What is the current immediate state of the system? Background. What relevant events happened over the last 12 hours to lead us here?
Assessment. What is my analysis of the current risk picture?
And recommendation, what exactly do you, the incoming operator, need to do, monitor, or escalate next?
The safety guidelines from the stainless steel manufacturer Acernox really hammer the necessity of this structure. They have a strict process safety framework.
Which is vital in that industry.
They highlight how incredibly dangerous it is to have active work permits, or to have safety-critical equipment, things like emergency shutdown valves or fire suppression systems bypassed or overridden during a shift change.
Esronox understands that overrides on safety-critical systems are sometimes necessary for maintenance. You have to bypass things to fix them.
Right.
But they mandate that any bypass must be registered in a highly visible log, explicitly discussed during handovers, and formally reviewed by management every 24 hours.
To prevent it from fading into the background.
Exactly. The failure mode they are combating is the reliance on human memory, or the vague, informal, verbal assumptions like, oh, I left the pump in manual override, but Sarah knows what to do, she'll handle it.
Sarah knows what to do is not a safety strategy.
It really isn't.
Esronox specifically calls out line-breaking operations, where you are physically opening pipes that contain hazardous, pressurized chemicals as highly sensitive.
For these high-risk operations, the active permit review requires mandatory face-to-face communication at the physical work location.
You cannot just leave a sticky note on a whiteboard in the break room.
Never. The outgoing supervisor must walk the incoming supervisor out to the equipment, physically point to the isolation points, verify the lockout tags, and physically confirm the system state.
Here's where it gets really interesting, tying back to our core theme. We mentioned another conceptual video used in industrial training.
Yes, this one is a classic.
It's called The Set Point Gets Another Assignment. It shows a wide, static shot of a control area. Over several simulated shift changes, different hands wearing different colored gloves enter the frame and turn the main master control dial up just a tiny bit more.
Just nudging it up.
Every shift, they turn it up to compensate for an unseen drop in performance. Over time, the master dial gets worn, smudged, and pushed to its absolute upper limit. But in the background, completely out of focus, is the tiny, pristine, neglected local valve that is actually causing the system restriction.
Nobody is looking at the root cause.
They're just tweaking the master dial, glancing at the output, and writing running in the logbook.
That visual perfectly encapsulates the illusion. The word running becomes a linguistic garbage can.
A garbage can. I love that phrasing.
It acts as a broad, deceptive container that hides a multitude of sins. It lumps together a machine that is operating perfectly normally, a machine that is operating in a degraded state, and a machine that is barely surviving by the skin of its teeth after 6 manual workarounds.
And if running is the only option on your checklist other than stopped, you systematically erase all the vital evidence of deterioration. So we know the immense financial cost of reactive maintenance. We understand the physics of failure, knowing we have to look for ultrasonic friction long before we feel heat.
Right.
We've confronted the dangerous human flaw of normalizing deviance, how quickly we adapt to broken systems, and we see how the shift handover is the deadliest gap in communication.
The diagnosis is very clear at this point.
So what is the practical fix? How do we actually change the language of the front line?
The solution requires a highly practical, structural change to how we communicate status. We found a brilliant diagnostic tool proposed in our sources from a specialized engineering editorial, the Still-Running Abnormality Check.
The fundamental shift here is training operators to identify and categorize equipment that is abnormal yet running.
We have to completely destroy the binary check of running versus stopped.
And replace it with 3 distinct mandatory categories. 1, normal. 2, abnormal but still running. 3, stopped.
Adding that middle category, abnormal but still running, is a profound psychological intervention for a workforce.
How does it change the psychology?
It gives operators explicit structural permission to report a weak signal without having to declare a full-blown emergency or shut down the line. It lowers the threshold for speaking up.
Because you aren't hitting the big red button, you're just raising your hand.
Exactly. And crucially, if a machine is marked in that middle category, the operator is then required to complete a specific 6-step diagnostic check before they hand over the shift.
Let's role play this, okay? Let's walk through those 6 steps conversationally, applying it to a real-world example from the sources.
Sounds good.
Let's say I'm an outgoing maintenance tech, and I'm walking past a massive industrial cooling tower fan. I feel a slight vibration in the metal casing. Not enough to trigger the automated alarms, but I definitely feel it.
Under the old system, you just check the box that says running and go home.
Right. But under the new Still-Running Abnormality Check, what is my first move?
Step 1. Identify what changed. You don't need a thesis, just a clear observation.
Okay, so I write, noticeable structural vibration on the south fan casing.
Step 2. Compare it with the known normal condition. Why does this stand out to you today?
I write, normally this casing is completely smooth to the touch.
Perfect. That provides the baseline for the incoming shift who might not know what normal feels like.
Yeah.
Step 3. Record where and when it was observed. Be specific so the next person isn't hunting for it.
Okay. South casing panel, near the lower bearing housing. Began noticing it around 14 sever hours.
Step 4. Describe any adjustment already made. Did you try to fix it or did you just observe it?
No adjustments made. Left running.
Step 5. Escalate repeated or worsening observations. Is this a new issue or part of a trend?
This is the second day I've felt a vibration, but it seems slightly more pronounced than yesterday's shift.
And finally, step 6. Verify who will inspect it next. You cannot leave it open-ended.
Incoming reliability tech, Sarah, needs to take a specialized acoustic vibration reading on the lower bearing housing before 18 hours.
Notice the elegance of what just happened in that exchange. Implementing the 6-step check forces a structural change in the language of the plan.
It really does.
But more importantly, it completely removes the pressure on you, the operator, to diagnose the complex mechanical failure before reporting it. You did not need to know why the fan was vibrating.
Right, I didn't need to definitively state whether it was a failing bearing, a loose bolt, or an aerodynamic imbalance.
You just needed to report that it was vibrating, establish the baseline, and pass the baton clearly to the next person in the chain. It stops weak signals from disappearing inside that reassuring garbage can word, running.
I love how actionable that is. But let me push back a bit, or rather, zoom out.
Sure.
Does this apply if I don't work in a factory? Say I'm listening to this and I manage a software development team, or I run a global logistics supply chain, or even a customer service call center.
Okay, very different environments.
Right. There are no physical cooling tower fans in my world. Can I use this 3-state model and the 6-step check?
This raises an important question about the universality of systems engineering, and the answer is absolutely yes.
Really? How so?
Well, the 3-state model, normal, abnormal but still running, and stopped, applies to literally any operational system that experiences stress. Think back to Dan Liu's examples of tech infrastructure.
Oh, right.
If a cloud server's API response time slows down by 400 milliseconds, but it hasn't actually crashed and timed out, it is not normal.
It is abnormal, but still running.
Exactly. If a software deployment requires 3 engineers to manually run scripts to push it live, but the website stays up, it is abnormal but still running.
I can easily see how this applies to human teams, too.
Oh, absolutely.
If your customer service team is hitting their daily resolution metrics, so the dashboard looks green to the executives, but the team is working through lunch, crying in the bathrooms, and looking completely burned out.
They are absolutely abnormal but still running.
Right. And if management only looks at the final output, the fact that the code shipped, the packages were delivered, or the calls were answered.
They're operating on a run-to-failure model.
Wow.
They're waiting for the server to permanently crash or for their top 3 engineers to quit due to burnout.
That's a huge blind spot.
It is. Using this 6-step check creates a visible paper trail for friction in any domain. It forces leadership to document the workarounds, the emotional deviations, and the systemic stress before they cascade into catastrophes.
So what does this all mean? Let's bring everything we've unpacked today together.
Let's summarize the journey.
We started by looking at the sheer scale of the problem, the $119 billion toll of reactive maintenance, and the realization that running to failure destroys product quality long before the machine actually stops.
Then we explored the physics of breakdown.
Right, learning that we need POS frameworks and AI to listen for the ultrasonic friction, because by the time we feel the heat, the battle is already lost.
And we confronted the deeply ingrained human flaw of normalizing deviance, understanding that without psychological safety and structural reporting, our brains will naturally adapt to broken systems.
We saw how the shift handover is the deadliest operational gap, where unwritten assumptions lead to disasters.
And finally, we walked through the highly practical solution of the Still-Running Abnormality Check to capture those weak signals.
The ultimate takeaway here is about regaining operational visibility. Whether you are managing a deep-sea oil rig, a hyperscale data center, or a sprawling hospital ward, you have to build systems that actively listen to the quiet signs.
You have to create the procedural space for people to say, this isn't broken, but it's not right.
Predictive operational safety isn't just about installing better sensors, it's about engineering better communication.
Because catching weak signals allows you to operate proactively rather than defensively. It transforms your culture from one of firefighting to one of forecasting.
It means you gain back control of your time. It makes you the person who sees the iceberg while there is still plenty of time to turn the ship.
That's the ultimate goal.
We want to leave you with a final provocative thought today. We've spent the last hour talking deeply about industrial machinery, software architecture, and corporate factories.
But systems are systems.
Right. I want you to turn this diagnostic lens inward. Think about your own life, your personal health, or your close relationships.
It's all connected.
What in your life is currently categorized as abnormal but still running, that you have slowly, perhaps unconsciously, started to accept as normal?
That's a tough question to ask yourself.
It is. Is there a lingering physical pain you're just taking ibuprofen for? A recurring communication breakdown with a partner? Or a highly stressful daily workaround you're just ignoring because, hey, you're still getting through the day?
The deviance normalizes quietly.
Exactly. And more importantly, what happens if you don't write it down, address the root cause, and hand it over properly before it finally stops running?
Something to think about.
Something to chew on indeed.
Andy,
Thank you so much for joining us for this deep dive. Stay curious, keep looking for those weak signals, and we will see you next time.